Log on, tune in, find out. Another good idea from Cambridge.
Problems, and today I'm going to talk about something that has nothing to do with time. But maybe you can think about there's a fictitious times and something relaxes very fast. And this is a joint work with Jay Chu, Bjorn Enquist, and Masha Prodanovic, all of them are at UT Austin. So this is a Texas product, and you will see the reason we need to find oil and stuff. So the objective is the following. You can think about the objective from different directions. So here, if you think about, so let me approach this way. We have, at continuum, we have a conservation law written this form with a flux function that depends on P, which denotes pressure, and the gradient of pressure, and then it can vary pointwise. The right-hand side is a source term, and this is put into a domain. So far, this is written as a 1D problem where you have pressure on either side of the domain. And eventually, this we haven't done so far, eventually this equation has to be coupled with some time-dependent problem to simulate multi-species flows in some domains. This equation is going to be solved, but we assume that the flux function here is very complicated, so there's no analytical form that we can use in order to solve this conservation law. But instead, we assume that this flux can be evaluated from a network model which is defined with at much smaller length scale. So we assume that let's say we're given a piece of rock, and we would like to simulate a flow that passes through this rock. So the ground truth is the given network model, that model which is already a simplified model for the rock configurations. And you would like to simulate this network, the flow through this network, by solving the conservation law. But you don't have the analytical expression for this flux, so you would like to couple your solution of solving such a conservation law to the solution of solving a network problem. Which brings us to the second bullet point. The assumption is that this network is too complicated. So maybe at the length scale of, let's say, 10 meters or even larger length scale, that's the length scale that you would like to know the property of the pressure distribution. However, the network is describe something that is defined for a length scale at millimeters or even smaller. So the resulting network is going to be too large. So this might be either a linear or a nonlinear network that you need to solve, and that would involve too many unknowns. So maybe it's too difficult to solve such network problems. So therefore, we are looking at some kind of speed up by saying that whether we can compute the effective behavior of when you apply certain pressure on both sides, and whether these the distribution of pressure over this domain of interest can be approximated effectively by such a continuum equation. So if we go back and look at this conservation law defined as a continuum, one of the very important properties is that the flux should be zero when there's no pressure difference. So nothing should flow through when the pressure on both sides are the same. So we're going to use this property in our approximation. So this will come out in a couple of slides later. So you might have seen, for example, if you this thing called Darcy's law, which assumes that this flux is a linear function of the gradient of pressure together with a k over here. And if you're familiar with homogenization problem, which Human had talked about this morning, is that a usual challenge is that this permeability function k may be defined with at a very small scale like this. It may be periodic or it may not be periodic, and it may have some randomness in this permeability functions. So it may be very difficult at the scale that you're interested in solving this problem. It may be too costly to solve the original problem with this this permeability function. So instead, you can rely on mathematical notion that you may try to homogenize the problem to come out with a homogenized permeability, so to get the epsilon scale out of the system, and then you can solve this thing over here. And then you see a lot of results related to the convergence of solutions with epsilon in there, to the solution of the homogenized problems. So related topics would be numerical homogenization, and then the implementation-wise or methodology-wise, you can think about multi-scale finite element methods, or in some situations you might need some kind of dual porosity methods that measure that kind of that's able to model situations where you have fractures appearing. So you have different scales at the network model. So this talk, in this talk, we're, as I mentioned just in the previous slides, is related to computing the effective flux or evaluating the effective flux of a network model that's defined at much finer scales. And then we're going to use the evaluation of such a effective flux to solve this conservation law. And then we're going to couple the pressure that's found by solving such an equation back to the network model in order to evaluate the effective flux. So there's a circle, and then of the flow of informations in such way. So this slide is supposed to tell you some challenges, why we are thinking about using network models as some kind of model for to study. Let's say flow passed through some complicated domain. So this is a piece of rock, and you can see that the black region corresponds to cavities in the rock, and here it's more, you have a lot of sands packed together. So these are microporous regions. So the space, you can imagine that the conductivity over here is more homogeneous. However, the conductivity or the permeability, this K function is homogeneous over here, but it's going to be very different in this region due to the kind of the geometry related to the fracture, or to, you have this macro or large size pores, or in some communities, these large size pores are called vugs, which came from rotten shellfish. So the shell occupies some space when sediments settle on the seabed, and then after a long time, the biomaterial is gone. So what's left is this very specialized shape, like horns or whatever. So there are different ways to obtain. So the thing is that once you get this kind of, you would like to simulate flow in this kind of domain. If you accept that network model would be a suitable thing to model such kind of configuration, then you need to be able to go from here to a network model. So there are a couple of different ways to obtain a network description of such media. One way is through some kind of molecular modeling. There's such a software package called SpherePax that would generate network for you if you prescribe certain material properties about the rock. Or many people do, you actually get, you drill into the earth and you get samples of rocks from different locations of the terrains that you're interested. You cut it up, or you use some kind of MRI or CT scan and get an image of the rock. And then, of course, the intensity of this image will represent the cavity or rock or different density of rocks, point-wise. Then from this thing, you do some image processing thing, and then eventually you isolate, the cavities, large area cavity, and then something which we'll call throat, which is a channel that connects, like this large opening to another large opening like that. And the black region is represented, usually is referred to this very high density rock that, water cannot penetrate, like that. So afterwards, you will get this kind of 3D network model. And I'll tell you, so here you see it's like a graph. You have vertices, and then you have connections between vertices, and these vertices are represented by spheres of different size and different colors because they carry different informations. And also the connections between each vertices is called a throat. And these throats also have to carry some kind of information that reflects the physics of the domain. And this is a slice, for example, of this thing over here. So there are already people who concentrate on, let's say, given a network model of such complexity, you would like to upscale, you would like to come up with a simpler network that kind of describe the effective behavior of flows passing through such a network. But that's not going to be the approach that we go through. We're going to use, we're going to use subdomains from these network models to help us evaluate the flux, which is governed by a continuum conservation law equation. So a little bit more into the network model. So in a very simplified setting, so these are the rock, and this is a pore, and the connection, the edge of this graph is throats, and the information that we want to carry at this during this talk would be each edge is going to be associated with a positive constant Cij, which is called conductance. Related. This term is kind of motivated from electric circuits. And the nodes are going to be enumerated. So, for example, this is the ith node and this is the jth node. And even at the network model, together with this constant over here, you can already write down some kind of conservation of mass written this way. So if we concentrate on the ith node over here and collect all the neighboring nodes that has connection to this ith node, and the amount of, if you put some pressure on both sides, then material would flow from, depending on the pressure, would flow from, if the pressure is higher from here to here, then the material is going to flow from this pore into that pore according to this constant over here. So centering at over here, this conservation of mass basically says what comes in will go out. So this is the formulation over here, like that. You sum over all the neighboring nodes like that, and then you should get 0. So if Cij is independent of P, then you get a linear system coming out. So you would get, for example, you see that after this, if the connectivity of each vertex in this graph is fixed throughout the network domain, then basically you're looking at you can write down the linear systems in a matrix, in a sparse matrix like that. And then it's very similar to this, whatever finite difference methods that you can think of on a regular grid. You cannot see this one over here. So here we comment a little bit about the conductance. So, as I mentioned earlier, in this simple network model, the only quantity that's defined over the network is the conductance, Cij, over each edge connecting each pair of pores. So this quantity has to have physical meaning, and also it has to, the location Pi and P of the ith node and jth node has to kind of incorporate something about the geometry as well. For example, if you have a Newtonian fluid in an experiment, you push this Newtonian fluid with viscosity mu through a tube of length L like that, and the radius is R, then you know the flux, the amount of substance, the rate of the amount of substance is flowing through this tube is linearly proportional to delta P, which is the pressure difference on either side of this cylinder. And then there is a dependence of r to the power 4 over here, and then this is inversely proportional to the length of this tube over here. So this is a constant, which is going to be summarized in this matrix C over here. And the boundary conditions that you put on either side of your network or on the sides of your network is going to be reflected in the vector on the right-hand side, B over here. So if you have a very large matrix, then this is related to the solution of such large linear system over here. The properties of such linear networks is related to all the coefficients here, either they're 0 or they're a positive constant, Cij. And because of this conservation of mass that we write down in the previous slides, then you can show that you can always invert this matrix, and there's a maximum principle which is referred to that the pressure value that you find in the on the nodes inside the network is going to be sandwiched by the boundary conditions that you put around the network. So these are the properties about the conductance and the network systems. Now we go back to take a look at the PDEs that we want to solve. So it's a conservation law in divergence form like this. So here I should have deleted this because this should be a 1D. Now I want to illustrate in 2D. So forget about this. Suppose this is your computational domain, then you can write this in in a finite volume approach, which means that you need to integrate the flux throughout the boundary of this control volume over here. And if you blow up this control volume over here, this means that you have 4 sides. So on one side on each side, you need to measure through the solution of the network simulations. You need to measure the flux that comes through this boundary over here. So effectively, the plan is the following: we perform, given the domain, continuum domain, we discretize it, and then we're going to discretize this equation by finite volume methods. And then we need to evaluate the fluxes needed by this finite volume methods on the sides of your control volume. And this flux is going to be solved by setting up a network model that's, say, maybe physically corresponding to the size of this orange box over here, with the boundary condition, the pressure on the vertical sides is going to be determined by the pressure variable, and the boundary condition on the horizontal sides of this orange box will be periodic boundary condition. So let's make it more precise. In the 1D setting, so this is just this thing over here is nothing but fj plus 1 minus fj j minus 1/2, and this is the right-hand side if you have a source or a sink. The value of this guy is going to be at the point xij plus 1/2 or fj minus 1/2 is going to be evaluated by some sample of the network, the originally given network, large network. You perform some kind of simulation with suitable boundary condition, and then measure the flux that goes through this network subdomain in order to evaluate this thing, and then you go up like that. So let's provide more details. So in an ideal situation, then this will be the continuum. The equation is discretized, and these are the grid points. So the cell size over here is delta x, and then we're gonna extract a thin slice of size smaller delta x from your network. So this blue line over here represents the network, and then the thickness of the network that we're gonna invert is going to be at every xj minus 1/2 is going to be of size delta x. So this should be considerably smaller than the original large size network. So you set it up so that the boundary condition of this network is on the left and on the right is determined by the solution of this now a discretized system for the continuum equation. You invert that matrix, Cp equals B, you get the pressure, and then from the pressure you can just compute all the compute the flux through this domain over here, and this will be the flux that is used to define the pointwise value of fj minus 1/2. So you're going to equate fj minus 1/2 to this lowercase f that is evaluated from the network model, and then we know that this function here is just we just denote that this quantity here depends on the boundary condition, and then the point over here. Okay, so yet a little bit more detail. So you see that from here, you need to know the value of the pressure in order to set up the network domain, in order to evaluate the flux, but you need the flux in order to come up with the pressure. So this is the circle of information over here. So we may need to break it into some kind of iterations in order to solve things, and hopefully the iterations converge. And I'm going to show you that for a large type set of parameters or settings, then these kind of iterations do converge. And what do I mean by these kind of iterations? I'm going to come up with an initial guess for pressures at my macroscopic discretization points. I'm gonna linearly interpolate those values in order to create the boundary conditions for my network domain. And then I'm going to solve this network problem and then evaluate the flux. For example, the flux, this will be a nonlinear flux. I compute all the flux through this domain, and I'm going to go up, and I'm going to say that the macroscopic flux at the next iteration is going to be the value that I just computed over here. But now I have this value over here. I need to, from these values, I need to come up with the values of pressures, I need to distribute those pressures on the macroscopic domains that satisfy the PDEs. But all this is done without the formal analytical knowledge about F. So how can we do that? So here we can rely on the assumption that the flux is 0 when there's no pressure gradient. So you can think about doing a Taylor expansion. So this function F can be approximated by, to leading order, can be approximated by a matrix K. And if you do have a linear flux, then this K would be the profession of this smaller K that I showed you earlier. Whereas in this case, our K is going to be approximated by the formula like this. That emulates the computation of this Jacobian. So you put this thing over here. Essentially, you approximate this flux by, you say that this flux can be approximated by some linear relationship with, with the pressure gradients like this. So this is how, given the flux value and the boundary conditions at the macro domains, you can go back and find the pressure at each one of the grid points, xj, xj minus 1, and then you distribute it, and this will complete how the iteration should run, and then you just let it run. You can, if you look at the continuum scale and how the scheme should go, then you can summarize the scheme, the iteration as the following, where the g function over here is going to be something like this. This is a center difference of fj minus the source term on the right-hand side like that. Whereas the value of fj is really approximate, as I mentioned earlier, is approximated by the network domain like that. And of course, the iteration converges when we find the roots of this g function over here. So in general, this iteration converge under some kind of suitable conditions. For example, if your network domain, this Cij, really is independent of pressure, so you have a truly linear network model, then you know that this G over here, the dGdP over here, in general, from here, in general, it has this form. And this is the K that we mentioned earlier. And if you have linear network, then this A equals to 0. So you're using, so our iteration method is like a Newton's method. So you would expect that it converges very fast. In fact, it converges in one step if you have truly linear network model. If it's nonlinear, then you can interpret this thing as some type of an iterative scheme that's in the style of quasi-Newton iterations. And of course, in order to prove convergence of this, you know how to get those kind of usual conditions. But in general, for the examples that we tried, we get convergence all the time. It seems to be pretty robust against the initial guess. So this is the simulations where we have, this is our, if you want, our ground truth. We build a network such, of 20 nodes in the vertical direction and 10,001 nodes in the horizontal direction. They look like that. The thickness represents how large the Cij should be. We're going to slice them up. These are the subdomains, subnetworks that we're going to solve in order to find the fluxes at different locations, like that. And then we might initially, just randomly distribute the positive conductance through the network, and then we compare our numerical simulations using this kind of multi-scale method to, to the solution of the entire network model. So here, if you have linear network, and with, when you don't do any, so when you use the network, so that the network domains that you use, they kind of, they are neighboring each other like that, then this is the error that you have. Or you kind of shrink it, you only use a thin slice instead of a fat slice, then you get this kind of error in pressure and in flux. Then in general, you can see that the error in pressure and flux kind of decreases. Let's see. They increase. They increase as your, so you see that this is, the error kind of increase when you chop it up into finer and finer slices. The more slices you chop it up, the error kind of increases. And the thinner this thing is, which means that if you look at it over here, m equals to 40 means that there's only 40 nodes in this across this distance over here. The thinner the network domain that you use to find your flux, then the larger the error is. So this can be explained because so far in our 1D simulations, we enforced kind of a constant pressure on both sides of the domain in the horizontal directions. So this will destroy the statistics or this will destroy the statistics of the connectivity of the graph of the underlying network like that. But in general, you get pretty good kind of error. This is nonlinear network model. You get similar behavior. So here on the network domain, even formally I told you that it's Cp equals to B, but now the C depends on P. So on the network, you want to solve a nonlinear system. So you can imagine that the computational gain would be in the, that you use a smaller size domain. But even here already, every time we solve a network from this chunk of network, and if you were to solve the entire network, then you have to solve a nonlinear system this big. So this kind of shows you, where you can expect gains from our numerical methods. And this is another type of nonlinearity I'll just flash through. This is when situations when you have some kind of source, delta sources at different points, or just sine functions defined throughout the domain. And here, this is some 2D simulations. This is the original kind of representation of our conductance. You have some barriers, so conductance equals to 0 in this regions. And this is just results from chopping this domain into different sizes. This is coarser 5 by 5 blocks, and this is 10 by 10 blocks, like that. And this is the contour of pressures that's being computed by the multi-scale algorithms like that. And you see that this is qualitatively similar to the full-scale simulation, like that. Due to the time thing, I'm going to just quickly fly through these slides. So now, at the moment, we're kind of studying, in a sense, how fracture appears. Because the logic goes, if you start out trying to if you apply pressure to the network on both sides, then the pressure is going to try to go into the cavities of this network. And maybe, the network configuration may be changed because of pressure. At some point, when you apply a very large, the pressure difference on both sides near a point is very big, then maybe the conductance will be bigger because the cavity will be pushed out. So currently we're looking into fracture modeling and incorporate this kind of fracture modeling into either at the network scale to modify our network, or to modify our continuum behavior because at a core scale. Because fracture can actually happen both at the pore scale, which is the network scale, as well as the continuum scale. And so this kind of situation has to be considered for more realistic simulation. And this, essentially, you need to, once you find the pressure, then you can define stresses in your network. And from the stresses, then you can find some formulas that tells you if the stresses are this way, then there are the tendency for the pore to open up will be larger. And then you use this kind of formula that we find from experts to do our fracture simulation. This is a simulation at the network domain where you apply, initially there is some large conductance over here. You apply a pressure, high pressure here and a low pressure here, and then you let it go through a certain iteration, and you see how fracture is being developed and branches off like this. In the future, hopefully next time when I discuss this, then this will be part of our multi-scale model like that. I will skip the slides and do a summary. So I would like to stress that this is a new work that we just started not long ago. There's a lot of things that we need to consider yet. And if you look at the proposed scheme, it is multi-scale of nature, the way it is designed, and is multi-scale. But if you think about the network domains that we use to simulate the flux value, they can overlap. So in this regard, then our method can be regarded as a domain decomposition method. if that network domain don't overlap, then they are like a subsampling methods for the network simulations. I think I should stop here, and I thank you for your attention.
Richard, any questions? Yes?
Is there a consensus in the industry on what kind of nonlinear relation between pressure and flow and
Yes.
vice versa?
Yes, I think the first consensus that I've heard is that in most situations, Darcy's law is sufficient. But if you want to be a little bit finer, then these are all possible nonlinearities that is considered by the experts. And sometimes you also need to add in some effect of gravity into there. But these are things that we dig out from papers and after consulting the people in this industry.
So the people that you are collaborating with, they include also the stress.
Yes. These are the flux. The stress is
The flux and the stress.
the stress is so the formula for stress is our approximation, but the threshold, the G function highlighted in the red is actually by experts. And then of course we need to design the numerical schemes that kind of incorporate how the pressure should be computed in order to and incorporate memory effect into this thing.
Okay, we thank Richard again for this.